All right. Well, we had a bunch of technical difficulties here, but I think we're maybe okay here. I got to get some pens. Today is going to be our last main day talking about groups explicitly. And then so on Friday, we're going to start talking about rings and fields, where you've got two binary operations instead of just one. You got an addition and a multiplication, not just an addition or a multiplication, but both. Does that mean rings and fields are harder than groups? Well, I don't know. I think that's somewhat of a matter of personal taste and opinion. Some people might think groups are harder. Some people might think rings and fields are harder. My personal opinion is I think the basics of rings and fields are maybe easier, but then when you get into the subject deeper, then it gets probably harder, especially when you get into the weeds on field theory, which will be the case, and this is just the way the topics go. Our topics the last few weeks of the course are the hardest. I will make them, try my best to make them as simple as I can by focusing mostly on examples, calculations, and that kind of thing. When you read the theory in the book, that's the place where it's extra tough. But the examples and calculations are certainly still pretty important. And they definitely do help you understand the theory, perhaps more than just reading the proofs do. Maybe you've experienced that with groups as well. And just want to emphasize that the calculations that we do, they'll actually seem somewhat simple as far as the calculations themselves go. But the implications that they have are much more profound than they might seem at first. So in that sense, it's kind of neat, you might say. But today I thought it'd be good to spend a little bit more time with groups, in particular with homomorphisms, and also with a little bit about chapter 11. Now, I'm not going to go into a ton of depth on chapter 11. If you did skim through chapter 11, you saw it was kind of a tough chapter, as they've all been, I guess. But I do want to highlight the main parts of it. And I think what might be good to do today is to just review chapters 7 through 10 with an emphasis on chapter 10, and then get a little bit into chapter 11. And just highlight some things. Highlight some things about our purpose. What's our purpose? Our purpose, again, is to try to understand groups, and that often means classify them. That's what a group theorist tries to do, is they try to classify groups by understanding them and by coming up with isomorphism theorems and that kind of thing. So let's just review, starting with chapter 7. Some more classification theorems, tax especially. So we'll just look at the book here for the moment. Lagrange's theorem leads us to our first classification theorem. Do you remember what it was without looking? Our first main classification theorem. It was a corollary of Lagrange's theorem. It's something about groups of prime order. They're cyclic. If you know the group has prime order, it's automatically cyclic. Groups of prime order are cyclic. In other words, it's if G is a group with order P, where P is a prime, then G is isomorphic to ZP, your standard cyclic group of order P. Doesn't mean the operation in G is addition, means there's an isomorphism. If you make their Cayley tables and you put the elements in the right order, they will match up, they'll have the same structure. So that's our first classification theorem. Second classification comes right in the next page here, page 145. If G is a group of order 2 times P, where P is a prime greater than 2, so P is 3 or 5 or 7 or 11 or 13 or 17, etc., then there's only 2 possibilities for G. It's either isomorphic to Z2P, meaning cyclic of order 2P, or it's isomorphic to the dihedral group DP, group of symmetries of a symmetric p-gon that would have p sides. So for example, if p is 13 here, that means we're talking about groups of order 26. There's only two up to isomorphism, Z26 and D13. Symmetries of a 13-gon, a regular 13-gon. By the word regular, I mean the sides have to have the same lengths and the angles have to be the same. It's got to be a symmetric kind of, pentagon or hexagon or octagon or whatever. P-gon in this case. Want to remind you about this theorem because we're gonna look at it here in a few minutes in an application. If you got two finite subgroups H and K of a group, define HK to be the set of all products H times K, where little h is in capital H and little k is in capital K. HK in general is not necessarily a subgroup of G, though in special cases it is. But you can still talk about how many elements are in it. If you're talking finite groups here, the number of elements in HK is the number of elements in H times the number of elements in K divided by the number of elements in their intersection. And that does, of course, then mean that if the intersection is just the identity, and it would have to be at least just the identity, right? Because both H and K are subgroups, they both have the identity. If it is just the identity, then H intersect K has an order of 1, you'd be dividing by 1. And you could say the order of this set here, HK, is the product of the order of H with the order of K. That's just going to be useful. It's not really a classification theorem, but it's going to be useful in something we're going to look at soon here. Classification with regard to the U groups in chapter 8. This came up on the exam. Ultimately, you can combine these facts down here with this fact here to classify any U group as either cyclic or an external direct product of cyclic groups. And you've done that before. That would then help you figure out the isomorphism class of it. The U groups are abelian, and we're going to see in chapter 11, which again we are going to talk about today. Chapter 11 is about classifying all finite abelian groups. All finite abelian groups. Really? All of them? Yeah, you can actually classify all finite abelian groups fairly simply. In the big scheme of things, and that's what chapter 11 is about. Abelian groups, not non-abelian groups. Okay, abelian groups are in general much simpler than non-abelian groups. Moving into chapter 9, do we have any classification theorems there? Well, this is a tool, the GZ theorem, that can help us do some classification. A lot of these theorems are just tools. They're just facts that might be helpful in the future with some sort of classification and might not. It's not clear in just looking at these theorems whether they'd be helpful. But it turns out they are. Somebody found that out by just doing a bunch of investigation. The GZ theorem, if the factor group there is cyclic, then G is abelian, which means if G is non-abelian, the factor group can't be cyclic. That has some pretty quick implications, actually, if you think about it. It would mean, for example, that if G is non-abelian, the center of G, which is, remember, the set of all things in G that commute with everything in G, the center, can't possibly have an index equal to a prime. This factor group can't be prime ordered, because then it would be cyclic, right? So that tells you something. It tells you something about what Z of G cannot be. So, for example, if G had order, say 33, what could Z of G not be if G is non-abelian? Well, it certainly can't be all of G, because then G would be abelian. It can't be order 3 or 11 either, though. I'm talking about groups of order 33 here. 3 times 11. It can't have order 3 because then this factor group would have order 11, which would mean it would be cyclic. It can't be order 11 because then this factor group would have order 3, which would be cyclic. So I guess the center would have to have order 1. It would have to be trivial. Any non-Abelian group of order 33 would have to have a trivial center. But wait a minute. That might beg a question. Are there any non-Abelian groups of order 33? I just said if you had a non-Abelian group of order 33, you would have to have a trivial center, and that might be useful. But that doesn't guarantee that there are any non-Abelian groups of order 33. This could sometimes be useful as another tool. This factor group is isomorphic to the group of interautomorphisms, just a possible tool. Cayley's theorem for abelian groups. Not technically a classification theorem by itself, but it's still an important theorem. If G is a finite abelian group and P is a prime that divides the order of G, then G does have an element of order P and therefore also a subgroup of order P. Right? Elements of order P would generate a subgroup of order P, cyclic subgroup of order P, in fact. Could be useful to realize. This seems to say it's only true for abelian groups. Actually, Cayley's theorem, or Cauchy's theorem, I meant to say, Cauchy's theorem does generalize to non-abelian groups. Let me just point that out. It's harder to prove in that case. Comes up in chapter 24, which we will not get into. Cauchy's theorem in chapter 24 says let G be a finite group, nothing about it being abelian, and let P be a prime that divides the order of G, then G has an element of order P and therefore a cyclic subgroup of order P. It does work for non-abelian groups as well, Cauchy's theorem, though you have to wait till chapter 24 to have the more general version because it's harder to prove that way. It's easier to prove in the case where you assume G is abelian. Here are a couple classification facts. Every group of order P squared where P is a prime is one of two possibilities. Either ZP or ZP squared or the external direct product of ZP with itself. And those two groups are abelian, therefore you have this corollary. A group of order P squared where P is a prime must be abelian. There are no non-abelian groups of order 121 because 121 is 11 squared. Here's what I want to spend a little bit more time on, go a little bit more slowly with, is these two examples. This is some hard stuff here. Example 16 and example 17 in chapter 10. Not going to try to spend the time to verify everything here, but let's take the time to make the effort to think about this somewhat at least. This is actually pretty cool. Ultimately, what you end up showing is every group of order 35 must be cyclic. 35 is 5 times 7. It's not a power of a prime, so we can't say that other theorem would imply that it's abelian. But we're concluding even more. We're concluding not just as it abelian, but we're also concluding it's really cyclic. That's certainly not obvious, thinking about it ahead of time. To do example 13, you got to understand example 16. And example 16 is it's an application of the first isomorphism theorem. Let H be a subgroup of a group G. Nothing about the group being abelian, nothing about it even being finite. Recall that the normalizer of H is this set. Now, we haven't talked about normalizers in class here, but let's go ahead and take a look at this anyway. What is this? This is the set of everything in G such that X capital H X inverse equals H. You've seen this kind of thing before. If that's true for every X in G, that would mean H is normal in G. Right? That's the definition of, well, it's the normal subgroup test, essentially. though with the normal subgroup test is just an inclusion. This is a subset of that, but actually they'd be equal. If this is a subset of that, they're actually equal. Do you remember this, that I said this before the exam? I said that whether a subgroup is normal or not depends on the bigger group that you're thinking about. You should always say H is normal in something. Draw a picture here. So if this is G and this is H, H may or may not be normal in G, but H is always normal in its normalizer. And the normalizer, N of H here, would contain H. Certainly if X is in H, then X, H, X inverse would equal H, because this set would consist of products of things in H, and H is a subgroup, it's closed. So certainly the normalizer of H contains H, but it could be bigger, but it might not be all of G. This could represent the normalizer. And even if H is not normal in G, it will always be normal in its normalizer, by definition of what the normalizer is. Thinking abstractly here, no examples at the moment. The centralizer of H and G is this set. We've talked about centralizers of elements before. C of A, you remember that? C of A is the centralizer of A is the set of everything in G that commutes with A, right? Remember that? Not the same as the center. The center is the set of everything that can, set of all elements that commute with everything. Centralizer of A is the set of all elements in G that commute with just the one element A, in particular at least. You can generalize the centralizer of an element to the centralizer of a subgroup. C of H is the set of everything in G that commutes with everything in H. If an element is in the centralizer, if it commutes with everything in H, it's got to also be in the normalizer. So C of H is a subgroup of N of H. And these things are all subgroups, by the way. So you could also add another layer in here. You could say, well, careful, C of H actually does not have to contain H itself. H might not be abelian. So this actually could be smaller than H itself. C of H in general, though it could contain some things outside of H, so I need to be careful here. So C of H is definitely a subgroup of the normalizer, but it's not necessarily a subgroup of H. That would be C of H. And what this NC theorem says is that N of H mod C of H, that factor group, is isomorphic to a group of the a subgroup of the group of automorphisms of H. Wow. Evidently, this mapping right there, and this is worth checking, and you have the ability to check this. You've got the knowledge. This mapping is an is a homomorphism, not necessarily an isomorphism. Of NH to odd of H, not necessarily onto even. And definitely not necessarily one-to-one. However, the first isomorphism theorem can come into play because C of H is the kernel of that mapping. That's worth checking. And that means this factor group is isomorphic to the image of N of H under this homomorphism it's talking about, where that maps an element G to its inner automorphism. Therefore, the first isomorphism theorem says you get this isomorphism. And you can say this is isomorphic to a subgroup of that. Okay, seems like a completely non-useful thing as far as classifying groups, but amazingly it's useful. I think for the sake of time, I don't have time to go through everything here. But let's highlight the argument. So you're trying to prove that any group of order 35 must be cyclic. Up to isomorphism, there's only one group of order 35, even though 35 is not prime. Let G be a group of order 35 by Lagrange's theorem. This is pretty basic. And every non-identity element of G has order 5, 7, 35, or 35. If you've got an element of order 35, you're done. It's cyclic. We're trying to show there that G is cyclic. So suppose to the contrary, it's now an argument by contradiction, that no element of G has order 35. So all the 34 non-identity elements would have order 5 or 7. However, 5 and 7 are prime. Any element of order 5 or order 7 has got to generate a cyclic subgroup of order 5 or order 7. And in fact, they all come in 4 at a time for order 5. If x has order 5, then so does x squared, so does x cubed, so does x to the 4th. X to the 5th would not, because that would be e. But 4 does not divide 34. So it cannot be the case that all the non-identity elements have order 5, right? Because they come in groups of 4. Groups in the usual sense of the word. Similarly, not all non-identity elements can have order 6. 6 does not divide 34. So there's got to be at least one element of order 5 and at least one element of order 7. And of course, there would then be more than one element of order 5 and more than one element of order 7. Let H be cyclic subgroup of order 7. Claim is it's the only subgroup of order 7. A little argument by contradiction here. If K was another one of order 7, then this fact would imply that that set has order 49, which is impossible because G has order 35. So there's only one subgroup of order 7. We've talked about this. This is a subgroup no matter what A is, and it's got the same order as H would have. H has order 7. Since there's only one subgroup of order 7, this must be true, and therefore H must be normal in G. And so its normalizer must be all of G. H is prime, so it's cyclic and therefore abelian. So C of H also contains H. This picture is not valid. The C of H would be bigger than H and contain all of H. So since H has order 7, 7 would have to divide the order of C of H. And the order of C of H divides order 35. So C of H has got to be either G or H. If it's G, you can get a generator. I guess this is not fully an argument by contradiction, by letting x equal H times K, where K is order 5, but that would take verification. On the other hand, if it's H, then this is order 7, that has order 5, but 5 does not divide that. And that's a contradiction. So a very intricate argument. It's hard for me to imagine coming up with this on my own. And if it's hard for me, then I'm sure it's hard for you to imagine you coming up with it on your own, but we can still appreciate it. The intricacies of the argument to conclude something you would never expect. All these tools in an abstract way are very powerful. We can appreciate this even if we haven't checked every single detail here. At least I feel I can appreciate it, and I hope you can. And I can praise God for this, that He has given us, with enough work, with enough time and effort, the ability to understand this, and gave somebody the ability to discover it in the first place. I think that's pretty amazing. God has structured the universe and people's minds in such a way that this is possible. Something you would never expect. It's surprising. All right, let's spend our last 23 minutes here talking about chapter 11. Keep saying every chapter is hard, and it's true. They do seem to maybe in general get harder as we go, but you're gaining some ability to handle it more as we go. Chapter 7 is called the Fundamental Theorem of the Finite Abelian Groups. It's a classification theorem. What does it say? It's right here. Every finite abelian group, we're definitely not talking about non-abelian groups here, is a direct product of cyclic groups of prime power order. Moreover, the number of terms in the product and the orders of the cyclic groups are uniquely determined by the group itself. So this seems to say something pretty profound. And by the way, the direct product could have just one factor, so to speak. In other words, the group could be cyclic, certainly. But how do you actually use it? Can you use this besides just appreciate it at a more abstract level? Yes, you can use it. We can, for example, try to figure out all possible groups of order, say 16, abelian groups of order 16. Looks like some people are writing, so I'll let you keep looking at this. I'll try to write at the same time. Suppose G is abelian. And the order of G is 16, which is a prime power, 2 to the 4th. Actually, this theorem by itself doesn't help us do what I'm about to do, but in conjunction with some facts we already know from chapter 8, I can do what I'm about to do. What could G be isomorphic to is what I'm trying to answer. What are the possibilities for the isomorphism classes? Well, certainly G could be cyclic. G could be isomorphic to Z16. We also know from chapter 8, though, that, for example, since 8 and 2 are not relatively prime, and 8 times 2 is 16, G could also be isomorphic to Z8 external direct product with Z2. Which, by the way, is also isomorphic to Z2 external direct product with Z8. Remember we talked about that before? When in an external direct product, as far as isomorphism classes, you can switch around the orders of the group in the groups in the external direct product. Is that the only possibilities? Can you think of another one? How about one that involves, say, Z4? What's one way I can finish this? Yeah, another Z4. 4 and 4 are not relatively prime. So this is not isomorphic to Z16. Could it be isomorphic to this thing? The external direct product of Z8 and Z2? Well, a little bit of thought. I hope you realize they could not be. For example, this group would have an element of order 8, whereas this group does not. So these two can't be isomorphic. This is a distinct isomorphism class. Or how about this? And again, the order of these things doesn't matter. This would be isomorphic to this. And also isomorphic to this. So those are not distinct isomorphism classes. Any more? You might also ask, are these definitely non-isomorphic? In both of these groups, the possible orders of elements are 1, 2, and 4. But I hope you feel like they should probably not be isomorphic. To prove it, maybe we'd want to count the number of elements of order 2 or the number of elements of order 4 using the LCM fact. Thinking about the order of an ordered pair being the LCM of the orders of the components. Also, that works with ordered triples. The order of an ordered triple, ABC, is the LCM of the orders of the components. So if you think about this group and say you want to count the number of elements of order 4, say, you can make a table. We're not thinking about the entire group here. We're just thinking about the elements of order 4. What are the ways you can get an LCM of 4? This could be 4, this could be 1, this could be 1, this could be 4. This could be 4, this could be 2, 2, 4, and then 4, 4. All of those give an LCM of 4. What are the number of elements in each case? In this first case, where A has order 4 and B has order 1, there's only 2 choices. A could be 1 or 3, and B would have to be 0. In the second case, there are two choices. In the third case, there are still 2 choices. A would have to be 1 or 3. B, to be order 2, would have to be 2. Still 2 choices here, but in this case, there's 2 times 2 choices. There's 4 choices. Because there's 2 choices for A and 2 choices for B. A could be 1 or 3, and B could be 1 or 3. On the other hand, in this one here, you got to think about ordered triples. You have to make your table bigger. We're still trying to come up with an LCM equal to 4. Oops, forgot that in there. Thinking about this one here. In order for the LCM to be 4, A would have to be 4. Because the only possible orders for B and C are 1 and 2. A was 4, and the order of B and C are both 1. The LCM is 4, and there are 2 choices. The order of A is 4, and this, 4 and this, or 4 and this. Those are the different ways you can get an LCM of 4, and in each of those cases, you have 2 possibilities. So while this group has 2, 4, 6, 8, 12 elements of order 4, this group has 8 elements of order 4. So those are distinct isomorphism classes. There's one more possibility to think about here. Or G is isomorphic to the external direct product of 4 copies of Z2. Which would have 15 non-identity elements that would all have order 2. So how many isomorphism classes are possible for an abelian group of order 16? 1, 2, 3, 4, 5 possibilities. And the book emphasizes that these 5 possibilities all correspond to what's called the number of ways to partition the number 5, which means to write 5 as a sum of positive integers. You could, I meant not the number 5, but the number 4, which is the power of the 2 here. You could write 4 as just 4 itself. You could write 4 as 3 plus 1, which is equivalent to 1 plus 3. You could write 4 as 2 plus 1 plus 1, which is equivalent to 1 plus 2 plus 1, or 1 plus 1 plus 2. You could write 4 as 2 plus 2. I probably should have put those in the opposite order there. And you could write 4 as 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5 distinct ways to write 4 as a sum of positive integers where you don't count these as different. Now, 3 plus 1 is not different than 1 plus 3. 5 ways to partition the number 4 corresponds to 5 isomorphism classes of a group of order 2 to the 4th. There would also be 5 isomorphism classes of a group of order 3 to the 4th, which is 81, since 81 is 3 to the 4th. There would be also 5 isomorphism classes of groups of order 5 to the 4th, order 625. I'm talking about abelian groups here, I meant to emphasize. Any abelian group of order 625, 5 to the 4th, is either cyclic, it would be Z625, or by analogy with this one, it would be Z125 external direct product with Z5. I'm talking about 5 to the 4 is 625 here. Or the external direct product of Z5 squared with Z5 squared, in other words, Z25 with itself. This would correspond to Z25 external direct product with Z5 again, and this would correspond to 4 factors of Z5 being the final isomorphism class of an abelian group of order 625. So we're talking about prime power orders where you look at the exponent and figure out the number of partitions, and that corresponds to the number of distinct isomorphism classes. You can actually combine this information to think about abelian groups that are not prime power order as well. Say we're thinking about an abelian group with order, let's say 2 cubed times 3 squared. 8 times 9 is 72. What are the possible isomorphism classes here? Well, once again, we can start with the easiest one. G could be cyclic. However, since 8 and 9 are relatively prime, I could also write that like this, since 8 and 9 are relatively prime. And that form of it is one form that corresponds to the statement of the theorem. I mean, this form does as well, but the theorem again says if G is a finite abelian group, what's the chapter? It's a direct product of cyclic groups of prime power order. 8 and 9 are prime powers, 2 cubed and 3 squared. But then you can break those apart, so to speak, just like we did before, and write things like this. G could be isomorphic to the external direct product of Z4 and Z2 with Z9. And these are distinct isomorphism classes because 4 and 2 are not relatively prime. Or G could be isomorphic to that. So I split apart the 8 in different ways. But I could also split apart the 9 in different ways. I could say, or G is isomorphic to, say, the external direct product of Z8 with 2 factors of Z3. Or G could be isomorphic to the external direct product of Z4 with Z2 with Z3 and Z3 again. Or G could be isomorphic to the external direct product of Z2 with Z2 with Z2 with Z3 with one more Z3. Forgot to turn my airplane mode on. Sorry. We had a lot of technical hiccups before class today. Does that make sense? 6 total possibilities. How does that correspond to partitions? You think about both exponents here. 3 can be partitioned in 3 ways. It can be just 3 itself. It can be 2 plus 1, which equals 1 plus 2. Or it could be 1 plus 1 plus 1. That corresponds to this table of 6 possibilities as having 3 rows. I was thinking about breaking apart the 8 as 4 times 2 or 2 times 2 times 2. And the number of partitions of the other exponent, 2, is just 2 of them. That corresponds to 2 columns here, which correspond to each of these, and then having a corresponding one over here where I break apart 9 is 3 times 3. And these are all distinct isomorphism classes. By the way, you can write these in other ways. For example, one other way to write that one is to combine the 2 and the 9 to write it as the external direct product of Z4 with Z18, because 2 and 9 are relatively prime. I could have combined the 4 and the 9 to write the external direct product of 36 with Z2, because 4 and 9 are relatively prime. Here I could combine one of the 2's with the 9. I could write this like this. Using the facts from chapter 8 here, because 2 and 9 are relatively prime. This one I could, for example, also write as combine 1, 2 with 1, 3 there, and another 2 with the other 3 there. I could write, say, the external direct product of Z6 with Z6 with Z2. I also could have just combined one of the 2 and 3's. I could write this as Z6 external direct product with Z2 with another Z2 and with a Z3. Gotta spend time with it. I am going to give you some practice problems to work on from chapter 11. I'm not sure about a graded problem yet, if I'll give you a graded problem or not. I'm not going to say you must read the proofs in chapter 11. I mean, I guess I haven't said you must read any proofs, but of course it's highly recommended to. The proofs in chapter 11 are extra challenging. The proof of the fundamental theorem involves actually 4 lemmas. It builds up the proof in terms of lemmas. Each lemma just comes into a piece of the proof of the main theorem. Lemmas are kind of tools to help you prove a bigger theorem. And those lemmas start on page 217 at the bottom. This corollary of this fundamental theorem is kind of an analog of the fact that if G is cyclic and M divides the order of G, then G has a subgroup of order M. Well, it works with any finite abelian group. If M divides the order of a finite abelian group G, then G has a subgroup order of M. This is not the same as Cauchy's theorem. M is not necessarily prime. Okay, so that's an introduction to chapter 11. You want to make sure you do study it, especially the first 3 pages. Well, let me say even 4 and 5, though pages 4 and 5 get into some things that I haven't talked about, especially the first 3. Okay. All right. Have a good day.